And you've been working at UW for many years, working on these crafts right here for many years. He's going to teach us all about them. And that's another good point. During the break, if you guys want to come up and kind of look at this, feel free to, but just be careful. Peter will give you guidelines. We don't want to hurt it. So, thank you. With no further ado, I'm going to turn it over to Steve.
Okay. Okay. Thanks everyone for coming. I want to introduce my partner. This is SG186. Okay. And thank you, Gwen, for having me. I understand that STEAM is science, technology, engineering, art, and math, right? Okay, so in this talk, there's going to be a lot of T, a lot of E, some S, no M, I promise. And I'm going to leave the A up to you guys to decide if there's actually any art in this topic. Okay, so I'm going to work out of order. I've got a lot of slides, by the way. I'll try to get through them quickly. Why does this thing exist? There's some grandiose statement about the world's ocean being the last great frontier, blah, blah, blah. Oceans drive climate. Okay, this is the important fact. The oceans are huge heat conveyors, and they have serious effects on climate, and that's the major reason that we're interested in what's going on down there. We can only typically see a tiny fraction of the ocean. We need more data. Ask any oceanographer what they need: more data. So how do we get data? Well, the problem is, there's the moon. 12 people have been to the moon. The Mariana Trench is the deepest place in the known ocean, 35,000 feet down. 3 people have been there. These 2 guys, Jacques Piccard and Don Walsh, he was a Navy captain, went down January of 1960. That was before I was born. 52 years later, another guy went down. Does anybody know who he is? Nope. James Cameron, the guy who made Avatar and Titanic. He decided he had too much money and he was going to have himself a custom-made deep submersible. And to his credit, he went down and he came back alive. So this is some recent news about ocean and climate. This was a story that ran in the UW paper just last week, actually. The bottom line is the Earth has not been warming up as much as they would have expected, given the models that were predicting back in the 1990s. If you look at the data, it turns out that we're not quite as warm as we ought to be. They're trying to figure out why, and these guys have figured out that a lot of that heat that really is being trapped by CO2 emissions is being pulled down into the deep ocean by the currents. So for people who are climate change deniers saying, why aren't we getting any warmer? Well, we are getting warmer, but a lot of that heat is not here on the surface. It's actually getting pulled down into the ocean. So we got to know what's going on down in the deep ocean. And this is how we used to do it. And actually, sadly, this is how it's still done to a large extent. These guys up here, that's probably from the early 1900s. They're operating something called a Nansen bottle. They drop it down on a rope deep into the ocean. It flips over, collects water, and they pull it up. This guy here is, oops, sorry about that. This guy's hanging out over the side of a ship. You can imagine how little of the ocean you can cover when you've got to take a ship out there and stand on station for hours while these guys do this. And it's really expensive. This is the University of Washington's research vessel, the Tommy Thompson. It's considered a global class, means it can go all over the world. Sits at a pier right outside my lab. Operating that ship, $35,000 a day. Excuse me, I'm having trouble with this pointer. Sorry, guys. Okay, $35,000 a day. Remember that number, because I'm going to talk about how much this guy costs. And you think he's expensive. So back in 1989, this guy named Henry Stommel was an oceanographer at MIT. He came up with this quasi-sci-fi idea of, instead of having these big expensive ships run around, what if we had just an army, a swarm of little robotic gliders that would run around the oceans and take all these measurements by themselves? And he got together with a guy named Doug Webb, and they concocted this thing called Slocum. Does anyone know where the word Slocum comes from? Joshua Slocum was the first man to sail around the world alone. So in the sailboat world, Joshua is probably the most common name in boats. And in the underwater world, Slocum comes up a lot. So they came up with this thing called the thermal glider. And remind me at the end of the talk to talk about that. I'm not going to talk about the thermal glider here, but someone remember? Okay, mental note. Ask about the thermal glider. Okay, very interesting. And then there were 3 of them. Slocum from Woods Hole in Massachusetts, Spray, which was concocted by the guys down at Scripps in San Diego, and our little buddy right here, Sea Glider. That's this guy. There are some others, not many. In fact, Spray is pretty unusual. There aren't many Spray gliders out there. The 2 big glider communities are the Sea Glider and the Slocums. And we sort of battle it out for who does more gliding. Here's a little bit of data about the Sea Glider. Development started back in 1995. There's a guy named Charlie Erickson at UW. Little eccentric, brilliant. I have to pay homage to our sugar daddies, the Office of Naval Research. They paid for this, okay? Start to end of development, probably in the order of $1 to $2 million, maybe $5 million. It more than paid for itself within the first couple of years because of the savings that these guys have generated over traditional oceanography. It's about 6 feet long, weighs about 114 pounds. That's important because it means 2 people on a small boat can carry this thing out, drop it in the water, and 6 months later they can go back out and fish it back out of the water. So the other gliders, the 3 I showed you before, they're all about the same size and weight. The battery capacity, don't worry too much about the number. The key, though, is that when we put this thing in sort of its sleepy mode, it uses so little electricity that it'll run on the order of 6 to 8 months. And that's the key. That's what makes these things special. They can stay out there flying around the world on their own 6 to 8 months before we have to go fetch them. And if you want to buy one, $100,000 bucks. That's a deal. Okay. By the way, I should mention there are other underwater vehicles that are not gliders. They have propellers on them. They look like torpedoes, right? Why don't we see more of those? Because the amount of battery capacity they have and the speeds that they run at, they last on the order of 4 to 8 hours, maybe 10 hours if we're lucky. And then the batteries poop out, and we got to bring them back and charge the battery. This guy flies around for 6 months, and that's really the reason he exists. So how does it work? I'm going to do a little bit of hand waving here, okay? The glider weighs about the same as seawater. So if I take this thing and I put it in the ocean, it doesn't want to float, it doesn't want to sink, it just kind of wants to hover in the water column. We have a balloon, which I'll show you, which we inflate and deflate, which makes it go up because it's buoyant, or makes it go down because it's heavy. So it's gravity fighting buoyancy. I'm going to skip ahead to another slide. Here's a very non-realistic picture of what goes on inside this thing, but I want to point out one, if I can find, sorry, I'm having trouble finding the pointer. 2 things. This little guy back here, it's a balloon that sits right back here. We inflate it and we deflate it. When it's inflated, it makes the glider more voluminous, same weight. It's now lighter than water, comes up. When we deflate the balloon by pulling the oil back inside the glider, the balloon collapses, the glider is now less voluminous, and it sinks. That's it. That's how this thing works. The other interesting thing here is this battery pack, and I'll show you a better picture of this in a bit. But the battery pack does double duty. It's not just the batteries. We actually move the batteries around to move the glider up and down in a roller from side to side. You'll notice there's no external moving parts on this guy. And that was a very deliberate decision. Anything that moves on the outside is going to break, and stuff is going to grow on it. So there's no rudder, there's no ailerons, there's no propeller. All the moving parts are on the inside. So I'm going to back up here real quick. How does it work? Well, imagine the thing is on the surface. It's sitting there like this, right? And we want it to go down. We suck the oil from that balloon back inside the glider. The glider gets heavy, and I got to do a little hand waving here. If anyone wants to see the math later, we can talk about it. The glider starts to sink, but it's got wings, and so we move this internal mass forward so it pitches down like this, and instead of sinking like this, it glides like this. Okay? Gets down to the bottom of the dive where we program it, say, 1,000 feet. We say we want you to turn around and come back up. It moves that internal mass back so it pitches up like this. We inflate the balloon, so now it's lighter than water. It wants to come up, but because of the wings, it doesn't go like this. It goes like this. That's it. That's the magic of gliding flight. So what's the big deal about that? It's the endurance. When this glider, excuse me, I'm going to flip ahead one more. Why do we bother gliding? It's extremely energy efficient. The only time we have to use any electricity is when we're pumping that balloon in and out. So you can imagine this thing is on the surface. We use a pump to pump oil back inside the glider. The balloon collapses. It starts to glide. At this point, we can turn everything off. Computer goes off. All the sensors go off. It's not using any electricity, but it's moving. And it'll keep moving until we turn it around and tell it to come back up. When this guy is in gliding flight, we put it in a special sleep mode where we'll tell it, don't even wake up but every 10 minutes. So while it's sleeping, it's gliding, it's sleeping, no electricity. It wakes up in 10 minutes, takes a measurement, goes back to sleep. Glides, wakes up, takes a measurement. And this is how we can operate these things for 6-8 months at a time. And I'm going to talk about another glider that flew a really long distance on a simple battery pack. The downside to this, gliding is really slow. How slow? Half a knot. Anybody know what a knot is? I know the sailors know what a knot. A knot is about a mile an hour. It's a nautical mile per hour. Half a mile per hour is the speed that this thing travels laterally. So if this thing is in a 3-knot ocean current and it's going half a knot, you can imagine what happens. It's just going wherever the currents take it. And for that reason, we tend not to fly these things near shore. We don't want to fly them near rivers. We certainly don't want to fly them where there's any kind of a tidal current unless we're there to babysit it. And sometimes, if the currents are too strong, we'll actually set the thing on the bottom and let it sit there so the current doesn't just sweep it away. Most of the time, these guys live their lives out in the deep ocean where the currents are very small. And a really interesting little side note, this guy was actually developed not to really go anywhere. He was developed to simply be able to hold station against ocean currents that were taking the existing measurement devices and sweeping them away. Then we got smart and realized you could actually make the glider go somewhere. So we have actually flown these things from Seattle to Hawaii. I'll talk about that in a bit. So another couple questions that people ask, well, how deep can this thing go? This glider is rated typically to about 1,000 meters. And for those of you who are metrically challenged, 1,000 meters is about 3,300 feet. Okay. The water pressure is pretty intense, 1,500 pounds per square inch of pressure at 1,000 meters. So how much is that? Anybody ride a bicycle? What's a high pressure bicycle tire? How much? 120. Okay, so that's more than 10 times that. That's a lot of pressure. It's trying to push water into this thing. So we've got a hull. This is just a plastic fairing. Inside that is the actual pressure hull. I'll show you a picture of that. Typical speed of half a knot, and our very sippy energy consumption is about a half a watt. So we say half a knot and half a watt. Maximum distance on one battery pack on the order of 2,000. I think we've actually done better than this. That's an old number. I think we've actually flown one of these guys 2,500 miles. I know we've flown one from Seattle to Kauai back in 2008 or so. Yeah, and we know where they are when they come to the surface. Another thing I should mention that makes these guys different from, say, spacecraft. I used to work in the aerospace business. So if you think of a typical spacecraft, like the space shuttle was able to get a satellite up about 350 miles. And a satellite at that altitude is flying along at about 17,000 miles an hour. We have constant communication with those satellites. This guy goes below the water that far, and he is absolutely invisible. We have no idea what he's doing until he comes up. And that's why we call them robots, because once they're underwater, they absolutely have to think for themselves. We can't talk to them. We can't see them. We can't hear them. They're gone. Okay, remember that. This is why submarines are so effective. They are pretty well invisible. Even in this day and age, there's almost no way to talk to vehicles when they're underwater. So we launch them, we let them go, and we talk to them when they come back up to the surface. I'll show you how that works. Yeah, right. So RF energy, like your cell phone, TV, radio, Wi-Fi, that's called radio frequency energy. Light, just does not penetrate water. It penetrates fresh water a little bit. We can see through fresh water maybe 10 feet with a radio antenna. Salt water is such an effective attenuator of radio frequency that once anything is about that far below the water, it's absolutely invisible to radio frequency. We can talk to them using acoustics if we're within a few miles, but that's the best we can do. Yep. This is the challenge of working in the ocean. So I'm going to try to get my slides to, oh, I'm sorry, let me come back here. So what does this thing measure? I mean, what's the purpose of having it out there in the first place? Well, the short answer is not much. We don't really need that many different kinds of measurements. What we need the measurements for, we need a lot of the same kinds of measurements over a long stretch of area and over a long depth and a long time. So the key temperature, by far and away the most important thing we need to measure. Just if oceanographer knew the temperature the way that atmospheric scientists know the air temperature, they would be ecstatic. In the atmosphere, we've got satellites, weather balloons, sounding rockets, weather stations, right? Satellites alone revolutionized weather forecasting. There is no equivalent in the ocean. So temperature, salinity, which is how salty the ocean is, dissolved oxygen, that's considered a fancy one. Optical properties, like how well you can see optically, that's pretty useless because in most of the ocean, within the first couple of feet, pretty much everything disappears. So optics doesn't work very well. And we get ocean currents indirectly because we know where the gliders went. We know how the currents must have swept them along. I want to show you something that is interesting, and I'm sorry if this looks like an economics class. I'm going to show you a chart, and I'm going to try to operate the pointer. So here's a, I'm sorry, I'm having trouble with my, hello. Okay, pointer. Never mind, I'm not going to use this. Look at that chart there. The red line, take a look at that red line. So depth goes down, okay? And the red line is the temperature. Look at the temperature way up near 0 depth. What does that temperature read? -1.5 degrees. And that's centigrade, okay? So that's just below freezing. And then it starts going up as you go down. So what's going on there? Anybody guess where the temperature would be that low at the surface and then actually get bigger? And another hint is look at the salinity. The salinity up near the surface is low, and it gets bigger as you go down. This was taken in the Arctic. This glider was actually under the ice. So up in the Arctic, where it's really cold, the freezing cold temperatures actually penetrated through the ice into the water up near the surface. And the water was actually below freezing. But that ice is also melting, so the water is relatively fresh. As you go down in this area, you go down in the ocean, the temperature is actually going up. That's really unusual. And then finally, you see the temperature starting to come back down. See this long curve here? This is typical in the ocean. And by the way, this 0 degrees C below about 700 meters, that's the temperature of the deep ocean everywhere in the world all the time. 0 degrees. No matter where you are, the tropics, the Arctic, Puget Sound, Gulf of Mexico, you get below about 700 or 1,000 meters, the temperature stabilizes and it stays at 0 degrees all the way down to the bottom of the Mariana Trench. Now, why doesn't it freeze? Pressure and the salinity, but mostly the pressure. Okay? Now, what's going on up there at the top is ice. That's frozen seawater. So this, I don't know if it's this glider, but a glider, and we do fly them underneath the ice. This guy came up, hit his head on the ice in the Arctic, and we do this typically. He made his measurements, and then we sent him back down again. And this is a relatively recent thing we've been able to do, is to send him around under ice. And here's how we do talk to it, when we talk to it. So glider comes up to the surface and sticks his butt up in the air. That's how we say it. The butt goes up. This is an antenna. This is a combination GPS and satellite telephone. So he gets his rear end up in the air, and he phones home. He actually connects to a computer in one of our labs. And I was telling these folks, he literally dials in using an old-fashioned fax modem. He's got a name, SG186, and a password. He logs in. He effectively types commands at the computer, sends his data up, and downloads instructions for what to do next, and then he goes back down on his next dive. So he's diving, gets down to the bottom, comes up, he's taking measurements all the way, sticks his butt back up in the air, and calls home again. These dives are typically anywhere from 1 to 8 hours, depending on how deep they go. And when they come up and when they call in, we're now at the point where we actually get a text message. So I could get a text message from SG-186 saying, hey, I'm at latitude, longitude, whatever, and I'm ready for my next dive. You want me to dive? And I could, yeah, go ahead, dive. Most of the time, we actually don't interact with them directly. We just send a bunch of instructions in a computer, and we say, just go that way. And go that way until I tell you otherwise. And they will just keep diving and coming up until they hear otherwise. They have safety mechanisms built in, you can imagine. If something goes wrong, the glider will, on rare occasions, decide that it needs to get to the surface and stay there. But we don't like to leave them on the surface. They're actually really vulnerable on the surface. I'll show you some of the things that happen to them. So we like to keep them diving. They're safer down in the ocean than when they're back up. And there's a sea glider on the phone. And this is just what they look like. They sit there, and it's pretty slow. This is where they're most vulnerable. They get run over by boats. People steal them. Sharks bite them. That's what it looks like on the inside. Right now, I just have the fairing. Some of the interesting parts are this green thing that looks like a, I don't know what that looks like. We call it the pupa because it looks like a caterpillar pupa. That's the pressure hull. That's the thing that actually resists the pressure of the water. And all the electronics go inside that. This is that battery I was talking about, the thing that slides around fore and aft on a rail. That's what pitches it this way, and then we can also roll it this way. So when we want to make this thing turn, we roll that battery pack. It makes the whole thing roll over like this, and just like an airplane, it banks over. And then when it gets where it's pointed, it needs to be pointed, it rolls the battery pack back and goes straight. We don't like to move that battery pack very much because it takes energy. So we're really concerned about how much electricity we use. And that thing back there is the balloon I was talking about. Grand total of 300 cc's of displacement. Not much. It's less than half a quart. That's our total ability to get heavy and light. It's made of a very heavy rubber. And this thing up here is called the CT sensor. I'll talk about that in a bit. And I can tell this is a really old picture because it says cellular antenna. So we don't use cell phones anymore with these guys. We talk over a satellite system. So here's some of the problems. Fresh water near the surface. The glider comes up. It's lighter than seawater. But if the surface water is really fresh, it's less dense. The glider can't get up through it. And we've had them stuck 10 feet below the surface. You can see them. Come on, come up. And we have contingencies in place for getting them when that happens. Heavy waves. If the guy comes up and he's trying to make his phone call with this thing sticking out of the water, but the seawater's crashing over him, it doesn't work very well. In those cases, we just automatically tell him, just go back down. If you can't get your phone call through, just go down, try again on the next dive. Shark bites, we've had them come back with half of this thing missing. We get tooth marks in them. I've heard stories that we've gotten them back with a shark tooth embedded in it, but I find it hard to believe because this is pretty tough plastic. By the way, the company that makes these wings and this fin specializes in making replica bones for the medical schools. And somehow we connected with them to make wings. I met them at a conference once. They had the wings and the tail fin next to a human skull, a replica of a human skull and a femur bone. The guy asked me if I wanted to put a femur bone on my glider. I don't know how that would work. Ship encounters, these are really bad. Sometimes they get run over. Not very often, but it has happened, and that's pretty much the end of the glider. And what we call biofouling. By the way, I've been out on ships where we're trying to find the glider and almost ran one over because they're actually really hard to see. The only thing that's visible is this stick, and we do have this handy dandy. When you guys come up later, you'll see there's a little sign on here what to do if you find one. So if you see one washed up on a beach or out in a boat, let us know. We are pretty sure that a couple have been stolen. We think one guy's got one up in his backyard on Cayman Island. But we don't have a warrant yet to go and look for it. And we think we know that because it was still sending GPS. Yeah. So biofouling. Well, this is a different glider. This is one of the Slocums I was talking about. Look at the stuff growing on this dude. That's a view from in the water looking up. This particular Slocum is really interesting. They named it Scarlet Knight. This guy flew from the east coast of New Jersey to Spain. One long transect back in 2009, and it was piloted by a group of school kids. In fact, it was a joint school kid venture between a school in New Jersey and a group of kids in Spain. Rutgers University builds these guys. You can see the crud growing on them. The big problem with the crud growing on them is it slows them down. So all that stuff is just drag. So I think they fished this guy out about 6 months into his trip and scraped off the worst of the barnacles and stuff and sent him back. The other problem with Slocum, unlike ours, he's got a rudder way back over here. And they're learning that rudders are a bad idea because that stuff grows on them and then they won't move anymore. Very hard to keep stuff from growing on these guys. The only paint that really works is also toxic. Oops, sorry, come back. Okay, so how do we get these things in and out of the water? Well, this is probably the most common way, a small boat. And typically 2 people can do this. I've done this. It's not easy on your back, but you can lean over and we just grab it by this guy and we heave it into the boat. In the water, it weighs almost nothing. Out of the water, it's about 100 pounds. In this case, I think someone called the Coast Guard, and we'll do this sometimes. If we have a glider that's running out of battery and it's somewhere out in the ocean, we'll call up whoever lives out near there and say, hey, can you send a boat out and get it? So we'll call up commercial fishermen, the Coast Guard if they happen to be there. A lot of times they're overseas. We'll call their Coast Guard. We have had a couple that were taken by fishing boats in Indonesia, and we had to pay ransom to get them back. Here's another example of one sitting on a ship. This is another way we often do this. More ship. Sometimes we have to swim with them. This is a guy that I used to work with, Keith. We had to put this guy in the water. He was having trouble with his buoyancy thing. We couldn't get it to sink, so Keith got in the water, shook it around a little bit, and finally it behaved. Another way we do this, and then this I don't recommend. We don't like doing this, launching them at night, but sometimes we have to. And here's one being launched off an ice floe. So we'll actually take them up to the Arctic and just slide them along the ice and drop them in the water. And I got some pictures here of sea gliders in various places. This one is up in Puget Sound. This is an early glider test, 2000. So this was at the beginning of we lost a number of them up there. This one's up in Alaska, and that's all we see when we go fetch them. That's all. And in big seas, it's really hard to see that. So we spend a lot of time driving around. That's why we like to put them out for 6 months, because it's such a pain in the neck to go find them. This is one. This, I believe, is the one that flew to Kauai from Seattle. Actually, I think it was launched in near Grays Harbor. So he flew about 2,200 miles. So he was ready. He was ready for bed. His batteries were just about pooped. And here's a homesick glider. We do test them occasionally in local waters. In fact, we had one recently right off of West Seattle. When we get them that close, we usually have a boat right nearby to kind of keep an eye on them. So where are they? They're all over the world. This is an interesting picture. You guys remember the big oil spill down the Gulf of Mexico back in 2010, the Deepwater Horizon? Well, we flew a whole bunch of gliders through that mess. People were really interested in what was going on temperature and chemical-wise. So we put chemical sensors on this guy and a couple of other gliders made by a couple of Slocums we had out there. And we ran them through the oil for months. Very, very useful data that we got back from that. I want to show you a quick picture of another glider. This is, we call it the Future. I don't know about the Future. I spent 8 years of my life working on that guy. Very different behavior, but the same basic idea. The advantage of that big wing shape is when this guy flies, he has to fly at a fairly steep angle, something like 40 degrees, because the wings are so small. That guy could fly at an angle of about 3 degrees, so he can go like this. So he can cover a lot of distance. And the other reason for that shape is this. Oh, gosh. Sorry. I'm challenged. I'm going to try to flick through this. Anyway, I got it, Glenn. I think I got it. Oops. Okay. Oh, what happened? Got it. It's up. Yep, thanks. So this leading, see the edge of the wing. Remember I said we can't talk to these guys? Well, that guy is actually fitted out with hydrophones, which are listening devices for sound. That guy finds whales. And the Navy actually wants to be able to detect marine mammals by their sound because they got a lot of bad press for emitting sonar. A bunch of whales got beached. the Navy is really, really sensitive now to marine mammal issues. So they want a vehicle that can hear marine mammals so that when they're testing their sonar, they could say, there was nothing around. And that leading edge on that vehicle is a really good place to put hydrophones. And that guy can listen for marine mammals, and that's basically what he does. Much bigger than this guy, you can tell. He needs a ship. He's still under development, and we're still trying to decide if there's a practical way to deploy him. This guy, anybody can drop off a small boat. That guy needs a ship. Yep. So that's kind of where we're looking at. That's kind of the future. There are other gliders under development. There's another one I should mention I don't have a picture of called the wave glider. And this guy actually, he's not really a glider. He just kind of scoots along the surface, and he's got this contraption that hangs down underneath, uses the wave energy to propel himself forward. And for the true geeks, that glider was developed by a company called Liquid Robotics, which was started by the man who started the Java programming language. Anyone remember his name? He also created the Emacs text editor for the real geeks. Anyway, it's a bizarre concept. Everyone said it would never work. I've seen them in action. It's amazing. They really do work. Yep. So I think that's all I got. And yeah, that's the current state of gliders. Thanks.
Awesome. Thank you so much. It was a fantastic presentation. Don't go anywhere yet. If you haven't signed in, please sign in the back, and please pay your $10. These events aren't free to put on. First and foremost, I want to compensate Peter. Part of where it goes. We're going to take about a 10-minute break. During that break, fill out your surveys. You have raffle tickets on your table. Fill out the raffle tickets. We are raffling off Amazon gift card and an actual underwater robot, slightly smaller than this guy. And then after 10 minutes, we'll reconvene for our question and answer. So make sure you have all your questions in order. And then after the Q&A, we'll do the raffle. So don't sneak out early.
And feel free to come up and you can't really hurt this guy. Just don't break off any of the fins. Yeah. That's it?
Don't hurt it. Awesome. So 10 minutes.
Yeah. It looks like it. Thanks for coming.
Our question and answer. And after the question and answer, I'll come around and collect some surveys and your raffle tickets. Also, for the question and answer, I would really appreciate it if you guys could use the microphone. So I have a microphone, and Michael back there also has a microphone. So just put a hand or a finger or touch one of our eyes. We'll get a mic. Thank you.
And does everyone come up and touch the glider? It's like Buddha. It's good luck. We have been concerned that when we fly them in the South China Sea, that China might make us think about that, but so far, no, because they're using them as well. We sell them to everybody. So they're not considered ITAR. If anyone knows what ITAR is. Yeah, they're not restricted. They're not considered, international traffic. Yeah. There you go. Thank you.
So the question I wanted to ask was whether or not you've done some cooperative projects with the Ocean Systems Group at Johns Hopkins.
Yes. In fact, we just hired one of their people.
Really?
Yes, a woman named Sarah Webster. So the question is, is everyone hearing the questions? Okay. Yeah, I know a bit about them. We work with them. They are, by the way, the other APL,
Right.
the Applied Physics Lab at.
They use equipment that my company makes.
Oh, what's that?
The name of the company is Metaquire. We make small special purpose computers.
You make? I'm sorry.
Small special purpose computers.
Oh, thank you. Well, interesting. Well, I didn't mention this. We have a small special purpose computer, which is so small and special purpose. The company that makes it has been out of business for 10 years. And just before that happened, UW bought up the last stock of inventory of that little computer, which is slowly dwindling. And at some point, we're going to actually have to switch over to a more modern, say, i.e. something later than 1990 technology. Yep. I'm sorry? Yeah. Oh, you want to sell some little computers?
I'll give you my card.
Okay. By the way, I did ask a question at the beginning. Someone was supposed to remind me about what was the thermal glider. Right. So Webb came up with this concept of a glider that didn't even need batteries. It would just work off the temperature gradient in the ocean. And that glider, and there are some, they're called thermal slocums, they actually use the warm water at the surface and the cold water down below to expand and contract that balloon. So they don't actually use electricity at all. Theoretically, they could run forever. But they do need electricity to run some of the little gadgets inside. And the other thing is they only work in places where the ocean temperature is much different at the surface than down below, like in the tropics. But up in this part of the world, and certainly as you get farther north, the surface water is so cold, it's not that much different from the water 1,000 meters down. So they don't work very well there. But it's a brilliant idea. And they do exist. I'm sorry?
What have these gliders learned from the Mariana Trench?
Well, the glider goes nowhere near the Marianas Trench, so it's much too deep. But we have had special purpose AUVs that are capable of going down that deep in the Marianas Trench, and we had gliders talking to them. And the way that the reason for that was the gliders, when they got to the surface, know where they are from GPS, and they were actually able to send acoustic signals, those are sound signals, all the way down to the vehicle, swimming around way down there. And from the time travel, the amount of time it took the sound to go from the surface down to those guys, they could figure out where they were. So we actually used the gliders to tell those vehicles where they were. And by the way, the speed of sound is such that to go from the surface down to 35,000 feet is on the order of 7 seconds. So if you hollered, it would take you 7 seconds for that sound to travel through the ocean. And sound in the ocean travels 7 times faster than it does in the air. So 35,000 feet, it's a long, it's almost 7 miles. By the way, Mount Everest, if it was sitting in the Marianas Trench, would still have 6,000 feet between the top and the surface of the ocean.
This might be the question you've read, but do you think that the missing Malaysian airliner we found in our lifetime, will robots play a role in finding it?
Yes and yes, yeah. Actually, yes and no. I think if it's found, it's going to be found by survey vessels that are trawling with sonars. The AUVs just can't go far enough. So remember I was talking about this guy is would totally be of no use to finding that Malaysian airliner because we don't carry the acoustic technology to actually listen. What they do use are these propeller-driven vehicles that they can actually send down, and we call it mowing the lawn. They literally just run back and forth using sonar to try to find stuff. And by the way, the airliner's own pinger is probably long dead. So the only way they're going to find it is by making noise and listening for the return. They call it side scan sonar. Those guys can only work for about 8 to 10 hours a day before the batteries poop out. The amount of ground they can cover is so small that it's not practical. I think if they find it, and I think they will, it's going to be from a towed sonar. But it's a good question. People ask us this all the time. Can you guys help us find the downed airliner? I say, no, probably not. Yeah. Like in the water? I'm sorry, there's a lot of noise back there. Oh yeah, we're actively looking to detect like chemical sensors. Is a big thing that people want to know is what are the chemical properties of the ocean. Has everyone heard of acidification, ocean acidification? The shellfish here, particularly here in the Northwest, the oysters are dying at a rapid rate. Their shells are dissolving, and they're pretty sure it's because the ocean is becoming more acidic from the CO2 that's being pumped into it. So there's a lot of interest in pH sensors. The problem with these sensors, there's 2 problems. They tend to be big and heavy. And anything heavy we put on here is just going to make this guy sink. And they use electricity. So what's driving the technology now is just like computers, is making them smaller, lighter, and more energy efficient. So I mean, it's a good question. We have people working right now. We have a lab, actually, a chemical sensing lab, that's working on making chemical sensors small enough that we could actually put it on this guy. We get asked all the time by scientists all over the world, can you put my sensor on your glider? And we say, okay, show us. And they come in with a box of some contraption that's like, you know, it's as big as a TV. And we're probably not. I mean, we could put it on there, but it would sink to the bottom and it would stay there forever. Is that what you want? So the technology's there. It's just making it small enough and light enough. But yeah, good question. We'd love to put all kinds of stuff on here.
Have you looked at all at putting any kind of photovoltaics on the antenna so that, you know, when it's surfacing for communications, you feel the recharge on the batteries?
So what would we, I'm sorry, some kind of,
Photovoltaic, you know, so you're collecting solar energy.
oh, solar power.
When you're surfacing, like how long is the typical surface interval?
We don't like to leave them up there very long. So a typical surface interval is 15 minutes, only because we want to get it back down before something bad happens to it. Now, out in the deep ocean, that's not such an issue. I don't think the amount of area you need for solar power, unless you're in the severe tropics with the sun right overhead, I don't think we get anywhere near enough energy out of a solar device. What we could use, actually, there are these wave energy devices now that will actually use the energy of the vehicle going up and down. I remember as a kid, I had a watch from Seiko that powered itself by shaking. And so I thought, well, if they could do that, can't they put something on one of these guys to make use of the energy in the waves? It turns out that's not, again, it's not easy to do with something that's small and light. Yeah, our sponsors are asking us all the time, how can you make it go farther? You know, how can you make it go longer? And the battery technology has gotten so good that we have 21 D-cell batteries are what live in this thing. And that's enough to power it for 6 months, but it can't do much with that. So people have talked about all kinds of crazy stuff. Some people have asked us, could you put a little nuclear reactor in there? You know, satellites actually use them. They use radioisotopes. The problem there is safety. No one's going to let you put it on their ship if you've got a little.
They're still pretty heavy too.
Yeah.
How many of the various sectors are you currently deployed? And how does that compare to whatever you would need to be able to
They're really.
model is equivalent to the weather model?
Oh, yeah. Good question. So the number of these that are out there right now, I'm going to take a wild guess and say 300 in the world's oceans. And I asked that today with some people around my lab. The problem is that we sell them to everybody, and we're not the only ones who make these. Slocum are built in New Jersey. There's Spray. So a good wild guess is 300. To get the kind of coverage we have in the atmosphere, we need 1 million, at least. Yeah. The thing about the atmosphere is that the real killer is that the atmosphere can be looked at from satellites. A satellite can see almost half of the world in one swath. We cannot see anything from the surface of the ocean. There is no equivalent to a satellite, a weather satellite for water. You can't just stick your face in there and see everything. So it would be many, 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 many. That's the short answer. Way more than is ever practical, would ever be practical. Now, there are talk of micro gliders. People talking about building little gliders about that big that would really be swarms. The problem is that they're actually considered pollution because eventually they die and they land on the bottom.
I may have missed this, but if radio waves can penetrate water, how do you track where the weather
Where it's gone?
where it's not between surfaces?
So when it comes up, it gets a GPS. It's got a GPS receiver, so it gets a GPS fix, and then it radios over a satellite telephone where it is. So it tells.
I mean, like, this trajectory.
We don't. Now we have a model. We have what we call a hydrodynamic model, which is a fancy way of saying if the thing is pitched down at a certain angle and the buoyancy is set at a certain amount, we think it flies like this. And we've actually gotten pretty good about that. In fact, it's good enough that when we say fly from here to Hawaii, and it knows where Hawaii is, and it knows the bearing angle to fly there, when it comes up to the surface, it has an estimate of where it should be because of this theoretical model. It then looks and sees where it actually was, where it got, and it says, well, I went down, I should have come up over here, but I actually came up over here. It must be the ocean current that's pushing me sideways, and it'll correct its course on the next dive to counteract that. In fact, they even carry models of tides in here. So really good question. How do we know where it is when it's underwater? We don't know where it is. And it doesn't know where it is either. This is the underwater navigation is an ancient problem that no one has really solved. Even the big nuclear submarines with all their fancy equipment, they don't really know where they are until they come up. They have a lot of expensive stuff, inertial navigation systems and whatnot, but the truth is when they come back up to the surface. Yeah.
So you said some of them do have sonar that communicate with the robots that go deeper. Do you know of anybody, or is it possible to work on creating better sonar to eventually put really sophisticated sonar on?
Yeah, and we're working on that. So what's happening in sonar is just like your cell phones have now moved to these coded. This is more than you probably want to know, but the way that how can all these cell phones all be talking to each other and it doesn't interfere? You ever wonder? I wonder about this. And they use what are called codes, so little bit patterns so they're now looking at using that with sonar. The problem with sonar is, and it's a huge problem, is that the speed of the sound in the water changes with the water temperature and the salinity. So if you're here and you're trying to talk to somebody here, the sound actually goes like this. In fact, it can even hit certain kinds of temperature channels where it goes like this, and you don't hear anything at all. Submarines have used this for 50 years to hide. You can have a submarine 10 miles away, and if the water temperature profile is right, the sound will literally just bend around it, and it's absolutely invisible. So the answer is yes, we're working on sonar technology. By the way, there's another problem with sonar technology. There are certain frequency bands that are marine mammal bands, and we get in trouble if we make sound. Anytime we go out and do any testing with underwater acoustics, we have to get permits from Department of Natural Resources, from the Coast Guard, from NOAA, and it's getting to be more and more of an issue because they're worried about, we're going to confuse the whales and they're going to go swim off. Yeah. If anybody can solve this underwater acoustics problem, you'll be a millionaire. It's hard. Yeah.
So you don't know where they go when they're underwater, but for like this guy, how far does he travel on a single dive?
Good question. Let's say he went to anyone want to do some math in their heads? He goes down at let's say he went down at a 45-degree angle and he goes to 1,000 meters. So what is that? That's about 700 meters sideways and 700 meters up. That's about 1.5 miles on that dive. So typically no more than maybe 5 miles on a dive. Now if he's lucky, he's got the current behind him and then he comes up, he goes really far. On the other hand, we've had him, sometimes we try to get him to go in a direction where the current is going the wrong way and they go backwards. They come up on the other end of where they should have been. It's a really good question. We have problems getting them where they're going because we don't know what the currents are. Sometimes what happens is, this has happened to me recently, well, a few years ago. We're trying to get a glider from here to here. It turns out that near the surface, the current was really strong, and the glider was trying to fight a current. Well, it was going backwards. So at night, when we didn't really care where it went, we sent it really deep and had to come way back up. And because the currents down there were much less, it was able to make up this lost ground by doing one long, really deep dive. And that dive, he might have covered 8 miles. That's about it. So to go 2,000 miles is a lot of, in fact, there's one of the pictures here, if we can go back. This guy? I'm going to this one in the Gulf of Mexico. See all these little dots? Every one of those is a glider coming back up to the surface. So to cover that ground, he had to go, and he's going down 500 to 1,000 or 3,000 feet in every dive.
And then other questions are about the information that you collect. Is it put on like a database that is available?
Yes, absolutely. Yep. You want to, if you can write down IOP. I forget what IOP stands for, but it's a publicly available. You can see all kinds of plots of where this guy went, the temperature profile, the salinity profile. It's all out there on a website for everybody. Sometimes what will happen is oceanographers will use one of these things, and they consider their data proprietary until they write a paper. And after that, it's so if you've got insomnia and you want to look at temperature profiles in the deep ocean, have at it. I'm sorry? IOP. And there's more to it than that, but I think if you looked up sea glider IOP, I think it's open to the public. I'm not sure, but if anybody really wants some data, let me know. I can get you some. Sure.
You mentioned like a project with school kids. Are there other like citizen science?
I don't know. We haven't done that. That was done by Rutgers University. We probably should. I do know that every year at UW there's a couple of public relation events. There's one called Pause on Science, and there's another one called the Orca Bowl. And these are all aimed at kids to get kids into marine technology and this kind of thing. I don't know that we've actually had school kids piloting these guys. I should say that piloting these gliders, we say piloting, by the way, the guy sitting at the computer telling it where to go. The piloting app, if you will, is really primitive. And you sort of, I hate to say this, you sort of have to be an expert to use it. And that was not by design. I think that was more of it just kind of got hacked up that way, and no one really felt an urge to make it easier. The people who are using these en masse, like the Navy flies a whole bunch of these, and they have this special purpose interface that looks something like this that was developed by some people at my lab. So a guy can just push a button and say, I want the glider to go there. That's not been the case typically with there hasn't been enough of a user community really demanding a simple way to use them. There you go. I'm sorry? Just about 100, yeah, it's 80 to 100 depending on what you want. If you want one of these fancy oxygen sensors, that might add another $10,000. But 100 is a rough.
What are the most expensive?
Good question. So this little guy in the end here, he's not the most expensive. This is a very special antenna. This guy took literally years to develop it because it speaks both GPS and Iridium, which is the telephone system. That guy's $1,000. You want to buy one of these little guys. Probably the most expensive thing is that pressure housing. The pupa. The pupa is, and I should say a couple things about the pupa. So the green thing. You notice that shape? How it's not typically things that we put in the ocean are shaped like spheres or cylinders. That's kind of the most natural, simple way of resisting pressure. Well, that shape was developed specifically for a very specific reason, which is as you go down in seawater and the pressure increases, the water is almost incompressible. That means that if you take water and you squeeze the living heck out of it, it really doesn't change. It doesn't change its volume much, unlike a balloon with air, but it does compress a little bit. So if you don't compress at the same time, you become lighter than the water and you'll stop going down. This has been a problem with gliders, is you make yourself heavy enough to sink, but as you sink, the water gets denser a little bit, and suddenly you're not dense enough to get through it. So they developed that weird shape with the wrinkles in it to compress exactly the same rate that seawater does. It's called an isopycnal hull. There's a word for you. Remember that word, isopycnal. Squashes down the same as the seawater. I'm guessing that hull is a goodly fraction of the total cost of this thing. And nobody else wants to buy them except people who buy gliders. So. Yeah, who would have thought? Don't you want one of those?
Print one with a 3D printer and model one.
Yeah, actually 3D printing is an interesting People are talking about building components for these things on a 3D printer.
Where are these actually built at?
That's another good question. Originally, they were all built in the UW Oceanography department. 2009, the technology was licensed to, I think it was 2009. Don't hold me to that number. Sometime in the mid to late 2000s, it was licensed to iRobot. Does anybody know what the company iRobot makes? What? The Roomba vacuum cleaner, right? The little hockey puck shaped vacuum that runs around your house and cleans up. So that company bought the rights to build sea gliders, mostly because the university didn't want to build them anymore. We're not a factory. We don't have enough production capacity. iRobot was building them for about 3 years, and they finally decided this is not our business. You know, we build vacuums, we don't build gliders. And they recently sold the rights to Kongsberg, which is a Kongsberg, a Norwegian company that specializes in underwater technology, big underwater technology. So they're building them up in Linwood right now. When iRobot had them, they were being built in North Carolina. But Kongsberg builds them in Linwood. UW still builds a small number for our own use.
So you have a machine shop that can do
Yep, our machine shop in my lab drills out those. By the way, that's aluminum, in case you're wondering. And one of the technologies that is being investigated for gliders is changing from aluminum to some kind of a composite, like the 787 airplane. And I think I mentioned in one of the slides, there's another version of this guy, an experimental version, which is capable of going to 6,000 meters, which is 20,000 feet. They call it the deep glider. Now that guy has a hull that's made of carbon fiber. And the reason for that is if we wanted to send this guy to 6,000 meters and we made the hull out of aluminum, it would be so thick, it would be too heavy, we'd never get it back. It would just sink.
the seals. If the antenna cable's cast, we have to be reasonably expensive.
Oh, the antenna, well, this whole thing is expensive. That's a pot, we call it potted. So there's an antenna, just a bunch of metal windings in there, and there's epoxy stuff on the outside. And apparently it's a real art. I know the guy who makes these, or who used to make them, and he was like the wizard in the black hat in the back room. He cooked those things up, and he still told me that every 10th one just failed.
So you have the seals, those wires have
Oh, yeah.
pressure to get the pressure of it.
They're potted. Yeah. We use the term potting. Not that pot, it's a different kind of pot. Basically an epoxy that we plug the holes with and let it harden up. Yeah. We have had sometimes they leak, not very often. Sometimes this oil bladder thing, the oil inside springs a leak and we open them up and it's swimming with oil. We'd rather see oil than seawater. If we see seawater inside, we have a... Seawater, in addition to being high pressure, cold, dark, it's also one of the most corrosive environments you can imagine. So seawater and electronics are really bad. Oh, good question. The balloon is filled with oil. Right. Right, but the way to think about it, Christy, is so the oil, when the oil's not in the balloon, it has to go somewhere, right? We suck it into a reservoir that's in here. You can't really see it, but it's in there. It's a cylinder that holds the oil. No, there's a small effect. There's a very small effect that when the balloon inflates, the back end wants to go up a little bit, but not much. The important thing is that when the balloon inflates, the volume of the glider gets bigger, and so it wants to come up. And when we want the oil to go into the reservoir, we suck it in. And by the way, one of the things that we do is to save energy is we pull in just enough oil so the glider starts to sink. When it gets down deep enough, the pressure of the water on the outside squashes the balloon, and we just let that pressure push the oil into the reservoir. Then the glider gets down, and this is the important part. When the glider gets down to its maximum depth, this is where it really has to work. Now it's got to inflate that balloon against 1,500 psi on the outside. And that's where that little pump really has to try to push that oil out. We use a special, very special little high pressure pump to inflate that thing against all that water pressure that doesn't want to let it come out.
The balloon is outside the pressure vessel.
Correct. Yep. And I wish I had one. You could see it. It's a cute little thing. It's made of very, very thick rubber. And that was another issue, was coming up with a balloon that didn't leak seawater but was pliable enough that it would, that little balloon's got to expand and contract thousands of times over its life without leaking.
Emptying the balloon could be as simple as opening the valve and letting seawater pressure.
That's exactly what we do. Yeah, we use the term bleeding, by the way. We call it bleeding. You open the valve, all that saltwater pressure squashes the balloon. And I should mention, we do lose them. We've lost these guys. Remember that $35,000 a day ship cost? So here's $100,000. That's 3 days of ship time. So they are considered, I don't want to say expendable, but we do lose them. People lose them. There is no special safety device on this thing. For example, if it springs a leak, it's gone. Other gliders, the really sort of fancy special purpose vehicles, have these very special emergency recovery systems, like they'll drop a weight. Imagine you carried some weight along that was just enough to your balance, that if something went wrong, you just drop the weight and you would always come up to the surface. And we thought about that, but we decided it was not worth the cost and the effort to try to balance out the weight. Other vehicles have special, what they call Argos beacons. They can sort of let go of this little transponder thing that, it's like an EPIRB, floats around in the ocean and just says, here I am, here I am. We don't have him. If he goes dead, he's dead.
Why not put a locator beacon on it similar to what's used on crash locators? They're very power.
Where would we put it? And I mean, what I mean is, not only is weight an issue, but drag is a huge issue. Anything that sticks out from this hull, everything that sticks out on this thing has been thought about and measured, because remember, we're moving at half a knot, half a mile an hour. You put another little thing sticking out here, we might lose 10% of that speed.
You could put it in a fin.
In a fin? Yeah, then you have to make the fin pop off, right?
No.
Or you're assuming that you're on the surface.
No. Just like the pingers work on emergency, on aircraft recorders. The recording device is on the bottom of the seat for 30
Oh,
seconds.
you mean a bottom pinger?
Yeah.
Actually, we do have bottom pingers on a lot of them. Yeah, a pinger, by the way, is it's a device that when you trigger it or when it decides to go off, it just emits this ping, ping, ping sound. Some of our vehicles we put pingers on. For most of these guys that are going to be out for 6 or 8 months, it's not practical to put them in here, so we don't bother. There's not much room in this wing, actually.
Sure.
How many, so one AUV, how many trips do they generally do
In its lifetime or in one?
in its life?
Well, theoretically, we just keep. By the way, the batteries are not rechargeable, so we run them until the batteries die, and then we haul them in and we put a new battery pack in. Theoretically, they go forever. Parts wear out, and so we replace them. If one goes for 6, you can estimate if a glider lasts 6 months and it does, let's say they do 12 dives a day. That's 30 days times 12. What's that? 360 dives a month. So on the order of a few thousand dives in one deployment. Then we pull it out, put a new battery pack in. We kind of look. Sometimes we have to replace these guys because the sharks bite them. And by the way, one of the things we find with these things is when sharks bite them or stuff starts to grow on them, is we see that they're swimming cockeyed. We see it in the data that we're telling it to go from here to there, and it keeps coming up like this. And often that means that something got out of whack, something fell off, or a lot of stuff is growing on one side. Shark bite, yeah. Fish, we have seen them with suckerfish stuck to them, although they don't seem to really like that. Suckerfish don't like them. Someone had the idea of putting robotic suckerfish to clean off the stuff that grows on them. And I'm not here. Somebody right here in this room. Whose idea was that? That was Robin's idea. Yeah. All right, so you want to get on that, okay? Robot suckerfish.
Awesome. No last question?
I'll ask one more.
Okay.
So then with a pinger, is it possible to chart the path of the vehicle while it's submerged?
It would be difficult. You'd have to have a receiver you'd have to follow it around because the range of the pinger is only a few miles. So you'd have to have a ship following it to hear the pinger, which sort of defeats the whole purpose of the, yeah. So the concept of the gliders has really been, it turns out it's actually not that important that they go exactly where we tell them to go. What's important is that they go somewhere, and that we know where they went, and then we collect up all the data. You can imagine these things just sort of randomly flying around, and at least we have that data. So anyone's got a boat and you see one of these things floating around out in Puget Sound, it's got a little number to call. Okay, if you decide you got to pick it up, you grab it by this guy. We prefer that you just leave it in the water. If it's on a beach, definitely give us a call, okay, because we want to find it.
Awesome.
Okay.
Yeah, thank you very much.
All right, thank you.